Greetings, Global Impact students. This is Mr. Ellinger, and this lesson is on complex numbers. The learning targets for the lesson are to identify, graph, and perform operations with complex numbers, and to find complex number solutions of quadratic equations. Some essential understanding for you for the lesson. Every quadratic equation has complex number solutions that are sometimes real numbers. The imaginary unit is the complex number whose square is -1. So, I squared equals -1. I representing the imaginary unit, and I equals the square root of -1. The real solutions of a quadratic equation show the zeros of the related quadratic function and the x-intercepts of its graph. Well, some background for the lesson. The set of complex numbers includes imaginary and real numbers. Thus, every quadratic equation has solutions and some may be imaginary. Be aware of the common misconception that imaginary numbers do not really exist. Imaginary numbers were introduced to solve quadratic equations of the form x squared plus k equals 0, where k is greater than 0. The imaginary unit I is a number, not a variable, and is defined as the square root of -1. In general, you cannot order complex numbers since they cannot be graphed on a real number line. Complex numbers have numerous applications in many fields including engineering, science, physics, and computer graphics. So the complex numbers are based on a number whose square is -1. The imaginary unit I is the complex number whose square is -1, so I squared equals -1, and I equals the square root of -1. So here it kind of gives us an algebraic definition here. So if we have some positive number a, if we're trying to find the square root of -a, this is the same as the square root of -1 times a, which we can then break up into two separate radicals as a product, square root of -1 times the square root of a, and then the square root of -1 is I times the square root of a. Alright, so how do you write the square root of -18 by using the imaginary unit I? So radical -18, square root of -18, is equivalent to square root of -1 times 18. So we can break this apart into two separate radicals using what's called the multiplication property of square roots. So we separate this into the square root of -1 times the square root of 18. The square root of -1 is I now, we know it's I, times the square root of 18. So we have I times the square root of 18, and that square root of 18 simplifies down to 3 square root of 2, because remember, square root of 18 can be written as the square root of 9 times 2, which can be broken up into separate radicals. Square root of 9 is 3, square root of 2 cannot be simplified. So that's where the 3 radical 2 comes from. So then we just put this all together. The number that's outside of the radical can be multiplied with I, so we have 3i. 3i is 3 times I times the square root of 2, so that's how we write that. Okay, so take a minute, pause the video, and try these 3 problems, and then also think about the part D here, and I will give you the solutions to those. Okay, so our solution in A should be 2i radical 3. Our solution on B should be 5i, and our solution on C should be I radical 7. Part D says, explain why the square root of -64 is not equal to negative square root of 64. Well, the left side here, the square root of -64, this is where our imaginary unit comes into play. That has the value of 8i. And this negative radical 64 is saying the negative root of 64. The negative root of 64, the negative square root of 64, is -8. So there is what the left side simplifies to, 8i, and the right side simplifies to -8, and clearly they're not the same, not equivalent. Okay, so here it gives us a little more of a formal definition of what are called complex numbers. You can write a complex number in the form a plus bi, where a and b are real numbers. If b equals 0, the number a plus bi is a real number. So everything that you've studied up until this point can be classified as a complex number. It just doesn't have the BI part, the imaginary part. If A equals 0 and B does not equal 0, the number A plus BI is a pure imaginary number. Okay, so numbers that just have the A part are real numbers. Numbers that just have the BI part are called pure imaginary numbers. And then numbers that have both are called complex numbers. So you see a Venn diagram here that kind of illustrates that. The whole set of numbers, so every number that we have in existence falls within this outer rectangular region. And then those numbers can be broken up into either real numbers on the left, imaginary numbers on the right, and inside the imaginary numbers are those numbers called pure imaginary numbers. So everything that you've studied up until now falls into this category right here. So all the integers, irrationals, rationals, whole, all of those fall into this left side rectangle here. So you can see there's a whole nother world of numbers out here that you've never even seen before, called imaginary numbers. So in the complex number plane, the point AB represents the complex number A plus BI. So we have this thing called the complex plane, where the real part is the A coordinate and the x-axis, what we're used to seeing as the x-axis. And then the imaginary part is the second coordinate, and there's what's called the imaginary axis, and you can see that here to the graph on the right. So it says to locate the real part on the horizontal axis and the imaginary part on the vertical axis. The absolute value of a complex number is its distance from the origin in the complex plane. And the way that we calculate that is absolute value of A plus BI equals square root of A squared plus B squared. And so we can talk about the distance from the origin that a number is, right? And that's the absolute value of a complex number. So this red length here gives us the distance from 0, and that's called the absolute value of the complex number. So we're not going to do a whole lot with graphing these things and talking about this absolute value concept, but we want to be able to just understand the basics here. So a couple of examples here. What are the graph and absolute value of each number? So in A we have -5 plus 3i. So if we come over here to the graph, here we have our real axis, here we have our imaginary axis. So -5 plus 3i, the real part is -5, so we'll start at the origin and go over to -5. The imaginary part is 3i, so we will go up to 3i. Put a dot there. Okay, that's the point, or the value, the number, -5 plus 3i in the complex plane. That's its location. And then its absolute value is its distance from the origin. So we have, it's a distance formula essentially. So it has a value of the square root of 34. So it is the distance formula. We have this formula A squared plus B squared. It's really the distance formula. Remember, the distance formula is this: x1 minus x2 squared plus x y1 minus y2 squared. So it is the distance formula, only we don't have the 2x coordinates in here. And if you think about that, we're calculating the distance from 0. So we can go from these values, since x2 or x1, whichever one we want, is going to be 0. We only need to use the x and y coordinate, but now we're not calling them x and y, we're calling them a and b, a for the real part and b for the imaginary part. Okay, so the number 6i, we call that a pure imaginary number. There is no real part. So the real part in this case would be 0, so this is like the equivalent to 0 plus 6i. So we only just go up 6 from the origin to plot that point. And its value is 6, or its absolute value is 6, because it's 6 units away from 0. So we can define operations on the set of complex numbers so that when you restrict the operations to the subset of real numbers, you get the familiar operations on the real numbers. That might be a strange sentence, but let's kind of see how this plays out. To add or subtract complex numbers, combine the real parts and the imaginary parts separately. So it's kind of like combining like terms. If the sum of two complex numbers is 0 or 0 plus 0i, then each number is the opposite or additive inverse of the other. The associative and commutative properties apply to complex numbers as well. So here we have two examples. What is the sum or difference? So we're taking the complex number 4 minus 3i and we're adding to it negative 4 plus 3i. So the commutative property of addition says we can add the real parts together, 4 plus negative 4, and then we can add the imaginary parts together, negative 3i plus 3i. Now, when we add the real parts together, we get a 0. That's where this 0 comes from. And when we add the imaginary parts together, we get another 0. And obviously 0 plus 0 is 0. So we would say that 4 minus 3i and negative 4 plus 3i are additive inverses of one another. Okay, and that should make sense because 4 and negative 4 alone, those two are additive inverses of one another. And a negative 3i and a positive 3i would be additive inverses of one another. All right, in part B, we want to take the complex number 5 minus 3i and subtract from it the complex number negative 2 plus 4i. So this plays out just like adding and subtracting polynomials. The first step that we need to do is just go ahead and eliminate the parentheses. So we have 5 minus 3i. And then what we do is subtracting this complex number, we're going to add the opposite of these parts of the complex number. So we're going to add the opposite of negative 2, which is positive 2. We're going to add the opposite of positive 4i, which is negative 4i. So that's where the plus 2 and the minus 4i come from. And then we use the commutative property, 5 plus 2, add the real parts, negative 3i minus 4i, add the imaginary parts, and we get 7 minus 7i as our difference there. We can multiply complex numbers of the form a plus bi and c plus di as we would multiply binomials. So this becomes like a FOIL problem. For imaginary parts bi and di, bi times di equals bd, so the coefficients on the imaginary units, times I squared. But then I squared has a value of negative 1, so BD times I squared becomes BD times negative 1, which is negative BD. Okay, so anytime you're working and doing a calculation involving complex numbers and you multiply and you get I squared, we can use the equivalent of I squared, which is negative 1, for our simplification. So in this example here, we have the pure imaginary number 3i times the complex number negative 5 plus 2i. And what we use the distributive property. Okay, we have a number times 2, a sum in parentheses here. So we distribute 3i times negative 5, we get negative 15i. 3i times 2i is 6i squared. So negative 5i plus 6 times negative 1. Replace I squared with negative 1 because that's its value. And we get negative 6 minus 15i. And it's customary to write complex numbers in this form. So the real part is first and the imaginary part is second. On B here's an example where this becomes like a FOIL problem. We're going to multiply the first terms, 4 times negative 1, so we get negative 4. We're going to multiply the outer terms, 4 times negative 2i, that's where we get negative 8i. We're going to multiply 3i times negative 1, so we get negative 3i. And we're going to take positive 3i and multiply it by negative 2i, and we get negative 6i squared. Now we're going to simplify. I squared becomes negative 1, okay? And again, all we're doing is replacing it with its actual value, its numeric value. So we get negative 4 minus 8i minus 3i minus 6 times negative 1. And then adding all of that together, negative 4 plus 6, we get a 2. negative 8i minus 3i, we get a negative 11i. So 2 minus 11i is the result of that. And then here's another example here on C. Worked out. And this one, if you notice, winds up working out to be just a purely real number. So go ahead and pause the video and try this example here. Take the complex number negative 4 plus 5i and multiply that by negative 4 minus 5i and see what you get. Okay, so if we follow the FOIL process, we should get first terms 16, outer terms plus 20i, inner terms minus 20i, and last terms negative 25i squared. Okay, so we can simplify this a little bit. 16 plus 20i minus 20i, those will cancel out essentially. Minus 25 times negative 1. 16, and then here we have negative 25 times the negative 1, that's a plus 25, and that's going to be a value of 41. So those two complex numbers multiplied together wind up as a real number answer. In the last example, the product was a real number. Number pairs of the form a plus bi and a minus bi are what called complex conjugates. The product of complex conjugates is a real number. So in general, two complex numbers a plus bi times a minus bi have a product of a squared plus b squared. Okay, and this shows you how you get there. All right, what happens? You can use complex conjugates to simplify quotients of complex numbers. So this is going to be very similar to situations where we have, when we have a radical expression and we have, 2 over the square root of 3, we have a rule that says we don't want radicals in the denominator of our fractions, so we go ahead and multiply the numerator and the denominator by that radical to eliminate or get rid of the radical that's in the denominator. We're going to use that same concept here, or similar process. But we're going to use this concept of complex conjugates to do that. We don't want imaginary units in the denominators of our fractions. So here's how this works. If we take the complex quotient of complex numbers, 9 plus 12i over 3i, what we're going to do is we want to eliminate the imaginary number here in the denominator. So we're going to multiply the numerator and the denominator by the complex conjugate of 3i. And then when I do that, I get a new quotient of negative 27i minus 36i squared all over negative 9i squared. And we get the I squared here in the denominator, so that negative 9i squared becomes negative 9 times negative 1, which becomes a positive 9. We also have an I squared in the numerator, so we switch that to negative 1, okay, which will make this second term become a plus 36. So we're left with negative 27i plus 36 all over 9. And then we just switch, put our real part first, our imaginary part second. And then we can do what we would do in a normal situation if this was a polynomial or some type of expression that has x in it. We go ahead and reduce this fraction down, okay? And what we do is, what we're using is basically the distributive property that would say we can separate these. We can separate the numerator over the denominator into two separate fractions and then reduce accordingly. 36 over 9 reduces down to 4. 27 over 9 reduces down to 3. We still have an I there, so that's where we get the 3i. Okay, in part B, we want to eliminate the imaginary unit from the denominator of our fraction, so we're going to multiply the numerator and the denominator by the complex conjugate of 1 minus 4i. The complex conjugate of 1 minus 4i is 1 plus 4i. So here we're multiplying 1 plus 4i by the numerator and the denominator. Okay, and I didn't mention this in the first part, but this ratio of the complex conjugates has a value of 1. So we are multiplying our given ratio by 1. Okay, we're just being very creative in how we go about creating that 1, and we can do that, okay? So it becomes like a FOIL problem in the numerator and a FOIL problem in the denominator, and that's what we get here in this next step. And we get some I squareds in there, so we just replace those I squareds with -1s, simplify, combine like terms, and we wind up with an expression -10 plus 11i all over 17. And then they take it a step further and they go ahead and separate that into 2 separate fractions. And we should do this because, again, our answer is a complex number. Complex numbers are in the form a plus bi. Real part, imaginary part. So here is the real part, and here is the imaginary part of that complex number. Okay, so here's an application of imaginary numbers. What is the factored form of 2x squared plus 32? So 2x squared plus 32. If I go ahead and factor out a 2 for my greatest common factor, I get 2 times the quantity x squared plus 16. Well, up until now, we would get here and we would say we're done. Well, we're not done. Okay, we can factor x squared plus 16 into a product of 2 binomials, but now having imaginary numbers in them. Okay, and the reason that we might want to do this is because we might be asked to solve this equation, 2x squared plus 32 equals 0. Okay, and so we would possibly try factoring this. And before this, we would get here and we would be stuck. We would say, oh, this doesn't factor, so I don't really know what to do. Well, I can factor this now, but I need to understand that it needs to be factored into a product of complex numbers, not real numbers. Okay, not real number expressions, but expressions that have complex components to them. Okay, and this is how this would factor. Okay, now we're probably not going to be asked to solve this by factoring. We'll have some other techniques, and this is where when we're using the quadratic formula and we get to the point where we have some number. I'm just making this up. Like we might have -4 plus or minus the square root of -13 all over 2, and we get here and we say, oh, something's not right. I can't have a negative number under the radical. Well, what this means is, if you remember a couple lessons ago, we talked about the discriminant. The discriminant tells us that there are no real solutions in this case. So our graph of our quadratic is going to be a parabola that does not cross the x-axis. And that's true. There's no real number of solutions. What that means is that there are imaginary solutions. They don't cross these real number solutions aren't x-intercepts of our graph of our parabola in the xy plane. They're going to have solutions in the complex plane. We're not going to look at that, but there are solutions here. Okay, they're just imaginary in nature. So final concept here. Every quadratic equation has complex number solutions. Remember, complex number a plus bi. If a is 0, then we just have a pure imaginary number. If b is 0, then we have just a regular real number. And these are the ones that we're used to working with. So what are the solutions of 2x squared minus 3x plus 5 equals 0? Use the quadratic formula. Substitute all of our values into the quadratic formula. So we're left with 3 plus or minus the square root of 9 minus 40 all over 4. Simplify. 3 plus the square root of -31 all over 4. This radical can be simplified to I square root of 31. So we have 3, the intermediate step here that they do not write is we have 3 plus or minus I radical 31 all over 4. And then they take it to this final step again, complex numbers, a plus bi form. So they write it that way. They have the real part, and then they have, this is the b in front of the imaginary unit. So it would be standard to write it this way. All right, so we take the 3 in front of the plus minus over 4 as our real part. The plus minus, take the radical over 4, that's the b part, and then in front of I. So this is how we would write the solution to this quadratic equation. Real part, imaginary part. Okay? So understand, every quadratic can be solved. And technically, every solution to a quadratic equation is a complex number. Even if the solutions wind up being 3 and -3. Those are complex numbers. Every number is a complex number. So this totally changes everything that you've ever learned involving square roots before, now solving quadratics before. There are solutions to things like this, square root of -9. Your calculator is programmed to work with real numbers. That's why the calculator is still not going to do this. But we have other techniques that we can use to solve these things now. So this complex number system brings a whole nother branch of mathematics into play, and it's called complex analysis. Okay, and so if you're interested in this, you could do a little bit of research on the applications of this in engineering and some of the other things that we mentioned earlier, physics, some other science applications. Very cool stuff. It's complicated, but it's very, very cool. So if you want to check that out, you can. I hope you guys have a great day, and finally, do some math!